divide by n?
So yes. So the next thing I was going to say is there's a typo on question 2. So very good. It says the average x bar is the average, but the equation I give you did not normalize by 1 over n. Just today I posted an updated version. Great, good. So there's also another typo on question 4. It said the following 3 matrices. There are only 2 matrices, but that was even less confusing. So like after the lecture today, you should have no trouble doing any of them. It is quite reasonable or expected that you can do some of these things, operations inside Python. I will. So like everything involved in the homework and more, and everything we talked about so like inside NumPy, which is inside of so inside the linear algebra package for NumPy, which has all the operations built into it that you would need to do anything on the homework.
So for then questions like question 4, would you anticipate that we would go through and just do it in Python, or do you want us to do it by hand and then like check our work in Python or something?
So I'm totally fine if you just do it in Python, right? So it might be good to understand what's going on in these questions. On the quiz or the final exam, you will not have Python available. You might get asked to do something similar to one of these. It should probably, if it involves like actual calculations, like say taking an inverse, I'm not going to ask you to take an inverse on one of the quizzes. Later in the semester, we'll actually see one way how to compute the inverse. It's not a hard algorithm, but it's not something to really ask you to do on a quiz. But it'll be good to understand kind of what these operations are doing. But on the homework, you just need to run them inside Python and tell me what the result is. Kind of like on the first homework, I just wanted you to kind of practice doing a plot in Python, which was the 4th question, and it was hopefully not hard. Yeah.
So do you want us to not turn in like handwritten calculations for those last 2 questions? Do you want us to turn in like a Python then?
Sure. Yeah. So just showing me printout of the IPython notebook would be great. Okay. For instance, or write the short Python code. It's going to be just a few lines, right? Doing that would be great, especially if you make a mistake. The first homework, some people were initially taken off for not including the Python for question 4. We've refilled all those points. We shouldn't have taken off, but it's a good idea to attach it just to in case you make a simple mistake. If it's wrong, it's just wrong. But if it was a typo someplace, and we can easily spot the typo, you can get partial credit.
I was going to ask if you wanted the Python code included.
I would recommend doing the Python code. And again, you don't need to actually attach the code. I don't allow you to do that. Just to add a PDF. But so we aren't actually going to run the code. There might be something later in the semester. I'll have like a fun challenge where I'll ask you to actually try and maybe I'll ask you to turn in code that we can check to actually see how well it works. But the code is simple enough that we don't need to run it. Just in case you haven't done these things in Python before, my goal is just to kind of force you to actually do them in Python, so it's not totally foreign to you. So good. Okay. And then all right, so hopefully at the end of the lecture, we'll go through an example. Hopefully the internet won't not be working for me today as we try and do that. All right, so we were talking So we're finishing today the review of linear algebra, and I'm kind of pulling out the kind of over 2.5 lectures, the core, I'd say, are the most important things from when you take a full semester of like linear algebra. We're not going to cover things like Gaussian Gaussian elimination, but we'll cover the core notation and terminology and the concepts that will be most important for understanding the algorithms we'll be doing the rest of the class. Starting on Wednesday, we'll see our first more than the simple one-dimensional actual day analysis. We'll start on linear regression, and then we'll start looking at these extensions of it and how to think and model this using all of the machinery we've been building up throughout the semester. Okay, so with linear independence, it's important to think about these vectors, x1, x2, up to xk, and these are all in Rd, and here we'll think of probably, say, k less than d, although this isn't so important. We also have, so these are vectors, scalars, alpha 1, alpha 2, up to alpha k. These are all going to be just real values. They're scalars. And we're going to think of writing another vector, z, which will be the weighted sum of all the vectors xi by these alpha i's. And the important thing is that this will again be a vector in Rd. Okay, I can add and I can multiply this as scaling all values inside of the vector by this alpha, and so I can reconstruct new vectors in this way. You know, just if these were scalar values, this should be this shouldn't be weird, but this turns out to be kind of important to conceptually think about this, especially when k is less or equal to is less than d. Then some kind of interesting thing happen. And then it's useful to think about what's called the span of a set X, which are going to be all the vectors Z in Rd. So such that I can write Z as so this way for alpha I in. Okay, so this is the span, this is the space of all the vectors I can write in this way. And so this kind of describes often it can be, especially if k is less than d, it will be a lower dimensional subspace. It'll be a linear subspace. So I think of, if I'm in 3D here, it'll be this plane. It could be a plane, or it can be a line, a singular line that slices through or pokes through this three-dimensional space. And so this is important because this generalizes to higher dimensions. I can have this could be a subspace, which is, say, a 7-dimensional subspace. Maybe k is 7 and d is 100, defines a 7-dimensional subspace in this higher dimensional space. And so this idea of a span is important. Okay, and so we'll say that, and I think I defined a little bit differently before. We'll say Z in Rd is linearly dependent on X if Z is in the span of X and is linearly independent of X, independent if Z is not in the span of X. Okay. So like one more definition. We'll say if the span of X is equal to RD. Okay, so if the span of X is equal to RD, that means that every vector Z in RD is linearly dependent on X, right? So, it means I can write in this way every single vector in RD. In this case, K might be larger than D, K might be equal to D. Then we'll say then X forms a basis for RD. So we'll talk more about a basis for RD later, but it means that if the span equals everything, then X kind of forms a basis. Think of it as it allows me to write anything in RD using these vectors X. Okay, so I can already write like the simple basis of RD. Let's say a very simple example of, let's say, R4 is going to be x1 equals 1, 0, 0, 0, x2 equals 0, 1, 0, 0, x3 equals 0, 0, 1, 0, and x4 equals 0, 0, 0, 1. Okay? This is a basis because if I want to write any vector z equals z1, z2, z3, z4, then I just set alpha equals to alpha 1 equals to z1, alpha 2 equals to z2, alpha 3 equals to z3, and alpha 4 equals to z4. Right? It's just, these are just the coordinates of this vector z. A basis is interesting in that it does not need to be these vectors. Right? This just allows you just to write it in the original coordinate system that we're used to using, but this means we're not tied to this. Having been able to have a basis other than this means we're not tied to this coordinate system. We can represent what we're doing without being forced to use this coordinate system. And coordinates are kind of clunky. If I write all this out, it takes a long time. But I can just say, okay, I can just use a basis, and there's some alpha values which will make this work. Okay. Okay, well, let's look at a more interesting example of what's going on here. Okay, let's say that x equals x1, x2, where x1 equals 1, 3, 4. And these are in R3, and x2 is going to equal 2, 4, 1. Okay, and now let's look at two other vectors. Z1 okay, 3, 7, 1 is Z2, and Z1 is -3, -5, 2. Okay, so are either of Z1 or Z2 linearly independent of X, or are they so linearly dependent on X, on the set X? Yep.
Z2 is linearly dependent because it's the sum of x1 and x2.
Right, okay, so I can write Z2 equals 1, this is alpha 1 of x1 plus 1 x2, this is alpha 2. Right, so it's...
Oh, sorry, I was incorrect, because there's a 1.
Oh.
I missed that. Sorry.
So I can't do that. I can almost do that. That works with the first 2 coordinates, but not the third. Okay? Good. So this is actually a proof that it's not linearly dependent on x1, x2. Right? If I'm going to get the first coordinate and the second coordinate correct, I can only do that by setting alpha 1 and alpha 2 both equal to 1. But this will not give me the third coordinate correct. This would give me 5 here. Right? So that means Z2 is linearly independent. Okay? So in general, if you want to show linear independence, you can kind of make an argument like this. Really what you're doing is you're doing like a version of Gaussian elimination to do this. We're not going to go through kind of how to do this in the class. There's, hopefully you've seen Gaussian elimination. You try and put this in a matrix next to these, and you try and do elimination, and if you can, then you can, if you can eliminate the factors for this, it becomes dependent. If not, it's independent. But we're not going to go through that. It's a detour that's a little longer than I want to spend on this. All right. So how about Z1? How about Z1? Yep.
It's x1 minus 2x2, so it's dependent.
Yeah. So Z1 equals x1. This is a 1. This is alpha 1. Minus 2 times x2. Right? 1 minus 4, it's minus 3. 3 minus 8 is minus 5. 4 minus 2 is 2. Right? So I can write Z1 in this way. That means Z1 is linearly dependent. This is a not. Okay. Great. So if I ask you to try and do this, you'll have to kind of come up with these coefficients. All right. So if you, yeah. So kind of again, Gaussian elimination would give you an algorithm how to do that, but we're not going to go through. So like how to do that, right? So you can also ask, are the vectors just in X, so like linearly dependent or independent? And that depends on whether you can remove any of these and keep the same span. If you can remove any of them and keep the same span, that means there's one that can be made up as a linear combination of the others. Then they are so like linearly dependent. Otherwise, they are then they are linearly independent. That means every vector, you can pull out that vector and you cannot write it as a linear combination of the others. So X by itself is X by itself linearly dependent or independent? So does that definition make sense? I can ask for a set of vectors, are they linearly dependent or independent? I can either compare a vector to a set, or I can just ask it of the set. When I ask it of the set, I'm asking about every vector in that set. Yeah? So yeah, that's right. So if I want to make x2 out of x1, I'd have to scale the first coordinate by 2, but then this one's not going to match. 3 times 2 is not 4, it's 6, so I can't make this work. Okay, so these are linearly independent of each other. Okay. All right, so in kind of let me draw a picture just to help out again. I like to draw pictures. This one is actually a small kind of live what's going on, but I still think it's worth one here. Okay, and then I can draw each of these points. Right, so I've got, let's say I've got, this is going to be A1, this is 1.5. I flip the x and the y coordinates here, so let me just do this so it's consistent with your thinking. Okay, so this point is 0, 1.5. We've got a point at, let's say, 1, 1. And another point at 2, and this is A3 at 2 and 0.5. Okay? And so you can think of them as being, these points are like linearly dependent on each other because I can draw, there's a straight line which goes through and captures all these points. Okay? There's actually an equation. In this case, you can write up L is the line, y equals um, 0.5x plus 1.5. Okay, so I can write this line as this equation, and this captures all these points exactly. So this is true. These points are all like linearly dependent, or if these are not linearly independent of each other. If I wrote out A2, I can write it as a combination of these. So what's the truth, though, is that each of these points is actually a vector, and I'm allowed to scale by things like 0. So I can always, when I think about this geometrically, the way it's defined, I can always include the origin as well. I can include the point A0, which is not in the matrix at 0, 0, right? So even if this point was not exactly on the line, I could still write it as linear combinations of these two by scaling them out a little bit and then writing the line through there. So they would still be linearly dependent on each other, even if they were not exactly on the line. Okay, but this is kind of a good thing to think about in higher dimensions. If I was in 3-dimensional space, right, and you know, it might be more interesting that all 3 of them lie on a single line here. If the z coordinate was 0 for all of them, then that might be interesting. Or if I put the z coordinate so it was actually decreasing at a fixed rate, this would be a more interesting sort of example. But it's nice to think about. I think that's pictorially thinking about a line running through all 3 of these points is kind of what's going on in high dimensions when you have this kind of linear subspace. If I perturb one point just a small amount, let's say these are data points I've gathered through some process, some sensing process, and there was a little bit of error here. This is actually 1.10001. It would be not exactly on the line. So this thing about being low, kind of linearly dependent is like actually a pretty brittle thing. If I had a little bit of noise, it's not going to happen anymore. Okay? So this is not something you actually expect to see exact linear dependence in real data. Later in the semester, we'll quantify how to think about when you have a little bit of kind of, there's still a little bit of noise, but it still kind of looks like a lower dimensional subspace. Okay. And so that will be more common when it's almost on those things. And we'll see how to quantify these things and how to think about, well, should we include the origin or not include the origin here? These are the data points. I want to have something go through here, but I don't want to worry about this kind of origin point as being part of my system of equations that I can describe this data with. Okay? So the next terminology is the rank. Okay, given a set, let's say x1 up to xn, and so these are a subset, say, of Rd. Then the rank is the size of the largest so subset which are so linearly independent. Okay, so it's the size of the largest subset which are going to be linearly independent. In this example here, right, where I have 3 points in R2, the rank of this is going to be 2, because if I didn't have this point, they would still be, I could take out any of the points, take out any pair, A1, A2. A1 and A2 allows me to kind of cover every point I could with these 3. Adding in a third point does not allow me to increase the span at all. Okay? In this example here, x1 and x2, right, the set x1 and x2, the rank of this example is going to be 2. The points are already, so they're already linearly independent of each other. So if I remove any one, I'm decreasing the size of the span. I can't represent as much anymore. If I were to include, if my example were x prime, or let's say, let's call this uppercase Z, and this were equal to x1, x2, z1, right? Then the rank of this set would be what? The rank of this set is 2, because I know I can remove z1, or it turns out I can remove any of the points in this case, and it's going to give me the same span, right? There's a subset of size 2 which is linearly independent, but the full 3 points are not linearly independent. These are linearly dependent. So the rank of this, so I'd write rank of Z, or Z, is going to be equal to 2. And here I'd say the rank of X is also equal to 2. Yeah.
So Z is kind of like those ranks can be used to like define how many dimensions are in the subspace?
Yeah, yeah, that's right. It's, it's useful in some other ways that come up in numerical linear algebra and other, it's just a useful nomenclature as well, but it tells you how many dimensions are in the subspace you're in. Yeah. All right, so one kind of interesting thing about rank, I can think about a matrix now, which is in our n times d, right? So now this is an so like an n by d matrix. And some facts I know is the rank must be equal to the minimum of n, and must be less than or equal to the minimum of n and d. Okay, yeah, and why this is true is I can apply the rank on either the rows or the columns. I can define the vectors as either rows or columns, and it's going to be the same. Okay, so the rank of matrix is equal to the rank of the rows, and that's equal to the rank of the columns. Okay, so I defined it here for a set of these vectors, the rank. I can pull them out, but I can talk about the rank of a matrix as well. And this is usually how it's used, the rank of a matrix. And then I can look at the rows or the columns, and it turns out they're going to give me the same answer. Okay, so this is neat in that, let's say X is this really kind of tall matrix. I call it tall when the number of there are n rows and d column, and n is going to be, say, much bigger than d, or even just bigger, but just to say is much bigger. And so I know that the linear combination of the rows, I never need more than d rows to kind of tell me the whole span, because the columns aren't so like too many columns, right? Each row here is d-dimensional, so I never need more than d of them, or I'm going to fill up the entire subspace. But if there is some sort of pattern going on here, some subspace defined by these columns, let's say I only need d minus 2, which is k columns, to give me to define the in order to define the basis, then I still only need d minus 2 of the rows to define the basis as well. Okay, and we'll kind of you'll get some understanding of why this is when we talk about dimensional reduction. We get into the singular value decomposition and the eigen decomposition, and it'll give some explanation for why this has to be the case. Okay, and so if the rank of X is equal to the min of n and d, then I say that X is going to be full rank. Okay, if it's full rank, then I can't do any sort of like dimensional reduction to a lower dimensional subspace, at least in terms of the minimum, other than, yeah. So that means for any vector z, I can describe it as a linear combination of the d of the any whichever is the minimum. So any d-dimensional thing I can describe as a linear combination of d of the rows. Okay, so again, hopefully this isn't entirely new for you. Otherwise, probably a lot of concepts coming at once. But we'll kind of see these in action later on in the semester. Okay, so the next really important thing I need is going to be the is going to be the inverse. The inverse is an operation I do on a matrix. So first say I have a matrix that is n times d. It is what's called square if and only if n is equal to d. Okay, so I have to have the same number of rows and columns if it's going to be square. Okay? And so I can only invert A if it has to satisfy two conditions. It has to be square and it has to be full rank. Okay, so it's not defined if the matrix is not square or it's not full rank. Okay, so this is one of these operations. And so then the property that the inverse has, so I write the inverse as, so inverse of A is A to the power minus 1 is usually how you would write this. And so it has the property that A minus 1 times A is equal to I, where I is the identity matrix. Which is going to be ones on the diagonal and zeros everywhere else. Okay, so this is simple. So I in R3, and so anytime you're doing linear algebra and you write uppercase I, it almost always refers to the identity matrix. Just in, let me write up a small example. Okay, great.
You wrote transpose, but you probably meant to write.
Yeah, great. So thank you. Yeah. So I can do this. Remember, multiplication in general is not going to be so commutative. So if I switch the order of operations, it's not always going to give me the same thing. And in this case, it's going to. Okay, so the inverse works the same way as you want to use this, think of it the same way you would taking something to the minus 1 power in, so if you're working with scalars, right? And so if you recall, if I have alpha, it's a real number, then alpha to the minus 1 is 1 over alpha. Right, so this means if I multiply alpha times 1 over alpha, it should equal to 1. Right, so let's say 7 times 1 over 7 is equal to 1. That doesn't matter what alpha is, as long as it's not 0. Then, again, this is not defined if alpha is equal to 0. Right? Otherwise, you're dividing by 0. The same thing, that's kind of what's going on here. If it's not full rank, then at some point I'm dividing by 0 in some way. Okay, and so so that's why kind of for now conceptually that's why it's not defined if it's not full rank. And so it plays the same role here, and the identity matrix plays the same role as the value 1, in that if I multiply something by its inverse, I'm going to get the identity. With scalars, I get the value 1, and that's the value on this diagonal. Oh.
Yeah, I was going to say that's also.
Okay. Good. Seeing who's paying attention here. So this identity matrix, the diagonal has to go from top left to bottom right. You don't usually go from the bottom left to the top right. That would change the meaning of all the rows and columns in some way. We're not, at least I'm not introducing how to talk about that right now. question about the inverse? We will, again, we'll see how to compute the inverse. So later on in the semester, if it's not square, if the matrix is not square, there's something called the pseudo-inverse that you can do, which kind of plays the same role here. And we can talk about how to compute that later on in the semester too. Well, once you have the eigen decomposition or the singular value decomposition, which we'll see later, then you can compute both these compute both these things. So okay, so and then I think this is the last review topic for linear algebra or orthogonality. All right, so we say two vectors, x and y in Rd, are orthogonal if the dot product is equal to 0. So this is the definition of orthogonal. Remember, this is the dot product is equal to 0. And intuitively, what this means is that, that if I look at these two vectors, x and y, that it's a right angle in between. Okay, they do not need to be on the orthogonal basis. They can be in high dimensions. I can look at this angle. I can define the angle in any dimension I want. And this angle has to be exactly 90 degrees. Exactly, so exactly pi over 2 radians. Okay, and if you remember that I could look at this angle and I could say that the cosine that the dot product between x and y is going to be the norm of y times the norm of x times cosine of theta. And what is cosine of theta if it's 90 degrees? It's going to be 0, right? So then it doesn't matter what the lengths are. When I multiply something by 0, it's going to be 0. What happens if it's 270 degrees? Cosine of 3 pi over 2. So it's also 0. That's kind of like saying if I'm measuring this angle instead, right? This is 2 pi minus theta, right? I can measure this angle instead. It's still going to give me 0, right? So that's fine. Okay, so this formula and this dot product allows you to kind of figure out if you're going to have a right angle between two vectors in high dimensions. I can calculate the angle this way. If I want to calculate the angle, right, if I just want to figure out what the angle is, it's going to be arc cosine of right, so I can calculate the angle in high dimensions in this way using some vector operations, linear algebra operations, and applying the arc cosine, which it's some lookup table built into your computer, but you can essentially compute this. Right. All right, so this allows me to compute the angle in any dimension. Yeah.
What might be the benefits of calculating the angle in a high dimension?
So I think I mentioned this example in the past of talking about this, but there's these common representation of so like one thing we'll see is that lots of types of data are ultimately represented as each data point is some high dimensional vector. And one kind of fairly useful way of saying how similar are two data points, one is often the Euclidean distance between them, but one that removes the scale notion of those vectors, which is sometimes the right thing to do, is just to look at what's called the cosine distance, which is 1 minus the cosine of the angle. Okay, and that's a very useful distance measure where there's ways of embedding kind of words in high dimensions, and basically if they're roughly 60 degrees or less, they're actually pretty similar because they're really high dimensional, so you can fit a lot of stuff in high dimensions, but if they're less than 60 degrees, that's probably pretty similar, where if they're, most stuff is close to 90 degrees apart, it's like 80 degrees or above. Okay, so that's one where you can do this, and this cosine distance was is kind of the way to think about that. Yeah.
So Euclidean distance is going to be susceptible if you don't like normalize your data, but it seems like you wouldn't have that problem. Maybe not with cosine distance. Is that correct?
Right. That's correct. So sometimes normalization can mean lots of different things, and in vectors that means normalizing make the normal 1. There's other notions of normalizing where you have all your data, so the mean is 0, and the standard deviation or the covariance matrix is the identity. And doing that can kind of mess with stuff in some weird way. So be careful which one you're talking about, but the normal way is to normalize the normal ways. Is the most standard way with vectors is to make them all so they're of norm 1. Sometimes you want to do the L1 norms one. Not necessarily if your cosine distance is what matters, but for some statistical kind of when you're treating these high dimensions as actually distributions, then it makes sense to enforce that the L1 norm is 1. That means that it's a discrete probability distribution. It means the sum of all the quantities has to be 1. And force them all to be above 0, and that's a probability distribution. Right? So there are lots of things you can do, but this is useful for when you're not thinking of probability distributions, and you want to measure angle in high dimensions. Okay, that's this. But orthogonal means they're completely they're kind of their angle is as basically as far apart as it can get. Essentially, you could make x so it's negative of y, and sometimes that means that it's actually further away from y. Sometimes sometimes x and minus x have the same meaning. We'll see some. I'll maybe talk a little bit about that soon. So if x and the negative are interchangeable, then 90 degrees is as much as I can get. If they're not interchangeable, which is the case with the cosine distance, then when I'm measuring stuff that way, then I can get bigger than 90 degrees. Okay, so let's go through another example. So let's say got two vectors, 2, minus 3, 4, minus 1, 6, y equals 4, 5, 3, minus 7, minus 2. Are these orthogonal to each other? In 2D, you could draw a picture and kind of see in 5 dimensions Yes, they are. Let's add these up. So if I take the dot product, I'm taking a product of the similar columns, minus 15, 7, 7, and do this right, and minus 12.
The third entry.
This is 12. 12. Okay, if I add these up, I'm going to get 8 and 7 cancel 15, 12 and minus 12 cancel. So the sum of all these is going to be equal to 0. All right, so that's really the only way you can check if they're orthogonal is to take the dot product. Okay, but that means that these vectors are kind of in some space. They're completely at a right angle to each other. So why is orthogonality so important? Is because we're often going to deal with and construct matrices which are full of or orthogonal vectors. Okay, so let's kind of, there's some some definitions here. So let's say V is a vector in R n times D. And so if the columns are all so normalized, so VI is equal to 1, and orthogonal, that means VI, Vj is equal to 0 for I not equal to j. Then this is what's called orthonormal. Okay? And if U is in R n by n, and we say all rows and columns are so normalized and or orthogonal, then we say that U is going to be orthogonal. Okay, so there's a slight advancements. Orthonormal, this does not need to be square. Okay, so I can have, generally this is used when you have, so D needs to be less than n here. I can have a subset, so these columns can be a subset of the rows of an orthogonal matrix. Right, so I could think of having a square here that's U, and then I took a subset of the columns. This can be V inside of here. So this can be orthonormal. U is going to be orthogonal. Just so so these orthogonal matrices are going to be very important because they're going to define this orthogonal basis of Rn in this case. So it means that either the rows or the columns in this case are going to give me effectively a new coordinate system of Rn, which I can use in place of the original coordinate system, where I just have these vectors, kind of every element of the orthogonal basis was 0, 0, 0, 1, 0, 0, 0, 0. Instead of using those, I can choose a new one instead if they satisfy this.
Did you need to write what the normalized bottom negative?
Or Yeah, so so this is supposed to be V, this is supposed to be orthogonal, right? So this is a stronger condition, this is a weaker condition, right? This can work for a matrix which is not square, the matrix V here, may only have D columns and n rows, where D is less than that. But every column vector here has to be a unit vector, and they all have to be orthogonal to each other. Whereas if I want to say a matrix U is orthogonal, it needs to satisfy it needs to be square, and it has to be still the rows, but also the columns, but also the rows have to be normalized, and and they all have to be orthogonal to each other, right? So it satisfies these conditions for rows and columns. Okay, and it has to be square. Okay, I couldn't satisfy this for rows and columns if it's not square, because I wouldn't, unless there were some like zeros. Like if this was all zeros, actually then those would not be orthogonal. I can't have more than, if D is less than n, I cannot have more than D or orthogonal vectors.
Is it possible to have a square matrix where all of its columns are orthogonal? Or sorry, all of its columns are orthonormal, but its rows are not?
That's a good question. I think that's not going to be true. Let me write up another property. Let's see if we can answer that. I think it can't be true, but so what we get is if U is orthogonal, then U transpose U is going to be equal to the identity, and also U transpose. Okay, so the nice thing about the orthogonal matrices, to get the identity, unlike the inverse, I don't need to do this inverse operation, which I told you was kind of messy. I just need to do the transpose. Which means that it's its own inverse. I don't know if there's a proof in there. I mean, if I just have this, if I just know this part, then I know that the transpose is the inverse. Wait, that right. So if I only know this fact, right, this implies that U inverse equals U transpose. If I can derive this side of the equation, then I know that if the columns are orthonormal, the rows must also be orthonormal. But I'm not totally sure. There's probably a simple answer to that, and I don't have it off the top of my head. So let's, this equation here is interesting because I basically know that the fact that it's normal, all the rows are normalized, means that if I take any row or any column, right, say, think of this as the set, in case U, then I know that UI by itself is the same thing as ui squared, and I know this is equal to 1. And I know that ui uj, where j, I is not equal to j, this has to be equal to 0 because they're orthogonal. So that's how I get this identity matrix, right? So when I do this multiplication by itself, I'm thinking of taking, right, so this is U transpose, and this is U. I think of this row is the column of U. Similarly, the column of UI. I know these are, so I'm going to get this identity matrix in the end here, which is, it's going to be square, and this will correspond with the cell right here, which is on this diagonal here. And I know when I dot these two together, it has to be 1. That means it's going to be 1 here, right? So that's everywhere on the diagonal. Whereas if instead I took UI and uj, right? So now this is going to give me something off the diagonal here. And these are orthogonal, so this has to be 0. So everything off that diagonal is 0, everything on the diagonal is 1. And so it kind of, you get this out of this, out of this definition. Yeah.
Is there a reason you have the square is equal to 1 instead of just that the length is equal to 1?
Well, I know the length is equal to 1, and so square root of 1 is 1. The dot product ui is actually the norm squared, not the norm. Right, so this is an equality, and this is equal to 1 squared, which is equal to 1. You just skipped a step there.
Was there a reason why you just not just put just drop the
I could have put a square root on here. If I want an equality here, in this case they're the same, but in general the dot product is equal to the squared norm.
Okay.
Right? So I wanted to write this general equality, this general property we have. Yeah.
I might just not be understanding, like, for right there where it says for I doesn't equal j. Why is the reason why we exclude where I equals j is that because that would be where
Yeah, so if I were to equal j, right, then you'd be getting this case, right? Then I'm taking the dot product with itself, and I know the dot product with itself is the norm squared of the vector. And these are not all 0. Right? Otherwise, they'd have to be the 0 vector.
Okay.
Yeah.
Is that or else that equal 1 then?
Yeah, it's gonna be equal to 1.
Okay.
Yeah.
Okay.
Right. Yep. So if I didn't have this condition, then it would be okay to not have this be true. What would the matrix be if, let's look at the orthogonal matrix, a little bit more restrictive. Let's say I had that, I did not have the normalized property, but they were all orthogonal to each other, all the dot products, and even I equals j. So I had instead that ui, uj, this is equal to 0 for everything, and I did not have this exclusion. Then what would the matrix, what property would it have? So if I did not have this.
I think it'd have to be 0, right?
It'd have to be the all zeros matrix, which is pretty uninteresting. Maybe it's interesting in that anything you multiply by becomes all zeros, I guess. But in that sense, it's very interesting from a mathematical perspective, I guess. But it doesn't do much useful for you, right? So I want to force this so that if I have the dot product of a vector by itself is equal to 0, I know its squared norm also has to be equal to 0. That means it's length 0. That means it's all zeros vector. Okay, so that's why I enforce this here. I mean, there are other reasons as well, but yeah. Okay. So what happens when I do? So I have some of vector x in Rn, and I do u of x. Let's just look at the norm of the u of x. Right? This is going to be equal, this multiplication, actually, well, let's just write this out. Let's say u has, I'm going to write this as u1, u2, up to un, has these rows here. This will be the most useful way of writing this. And this is going to be equal to so a new vector here, which is going to be u1 dot x, u2 dot x, un dot x. Okay, so we'll come back to this a little bit. Let's say this is u1 and this is u2. These vectors are orthogonal to each other. This is in R2, and I've got some data point here, x, and maybe there was some original basis here, right? So I can write down, this is the x1 coordinate, this is the x2. What's going to happen to x is it's going to get a new set of coordinates. This is going to be u1 x, and this point here, this length here is going to be u2 dot x. That's what this length is going to be here. So I'm going to give a new coordinate system. What's nice is because these were unit vectors, then the length here is this is a projection onto the closest point here. And this is a different orthogonal projection. So it means that I get these lengths here. But what's important about it is if I look at this vector, it's the same vector. I haven't, the result here is just in a new coordinate system here. And so importantly, I'm going to get the norm is going to be the same as before. Okay, so when I multiply a vector by an orthogonal matrix, I'm not changing its norm. All I'm doing is I'm changing its coordinate system. If I right multiply, the rows of u are going to give me are going to make up a new coordinate system defined by this orthogonal basis. It's going to be they're d vectors. They're all orthogonal to each other, so they're all linearly independent. Which means they're a basis, right? And they're orthogonals to be an orthogonal basis. And I'm basically just writing x in a new coordinate system, but I'm not changing it really. I'm not changing its length. I'm just kind of changing how I describe it. So so I can think of, because I'm going to write it as a new vector, it's not going to be here anymore. It's actually going to be moved in some way. I'm going to rewrite it. It's going to have these two coordinates now. This will be the first coordinate, this will be the second coordinate. If I were to rewrite these coordinates, I'm going to write, this is the x coordinate, it's going to come down here. The y coordinate is going to be up here. And this point right here, this is going to be u by x. What this has done, let me get my other color here. Because I haven't changed the norm, it's staying the same distance from the origin, which means that this is lying on some circle. Okay, oops, missed. Okay, it's lying on a circle, and this has rotated the coordinate frame. I've rotated the coordinate frame. It could be if there's minus signs, it might be a mirror flip someplace. Otherwise, it's a rotation plus maybe a mirror flip. But it's rotating the coordinate frame, so this point moves down to here. It's rotating down to here. Okay, so an orthogonal matrix, basically, think of it as rotating all the data. If I have 2 points, if I have another point here, it's going to rotate it the same amount here. So it's encoding these rotational angles. And you can derive these angles using using the dot products in some way. Okay, I want to see if I can show you very quickly in Python how to do this. Let's see if I have more luck today in the last 5 minutes here. Okay. So, and we'll spend more time thinking about this.
Just a quick question before you start. If there's another library that we're used to or that we like, that we don't fit in, are you trying to clean it up?
So sure, that's fine. Python's not a requirement. These exercises are meant to help you get used to Python because things will become super blurry. Let me put the other screen down. So a lot of the stuff now will be easier in MATLAB or in like R, but you can do it in Python, and trust me, it's not hard.
Much cheaper.
And well, R is free, and it's Octave is a free alternative to MATLAB. Okay, I guess we want to look on the one that's in focus, unless maybe my eyes are going here, but it's just possible. Okay, so where is my mouse? Okay, so there's this library called NumPy. You import it with this line. Okay, from NumPy. I'll make a shorthand. There's a linear algebra package called LA. I'll use that. You can set up an array just doing this, and usually you don't. And so if you haven't seen IPython or some version of Notebook before, this is the Google version. Just prints out this array, right? I can index an element into this array. Argue this is basically no harder than MATLAB, okay? There'll be some stuff it'll integrate with the rest of your program better than MATLAB will. It uses the same library most of the time. How it deals with sparse arrays is sometimes not as good. It has libraries built in, but I've had some difficulties in getting them to do everything they were supposed to do. But otherwise, it's usually calling the same backend. Okay, so you can print out the whole matrix. It'll always do it like this. If I print out a single element, right, this was, so I just nest the arrays to give me a matrix, right? Print out a single element. Let's see, this is 7. So this means I start counting from 0, right? This is the row 0, row 1, right? Row 0, row 1, and then the 0, 1, and then the second starting from 0 element is 7. Print out a subarray, very similar to how you do it in MATLAB. This gives me columns 1 through 3, but even though there's not a third column, it gives me just the first 2. Let's see if I change this to 2. What happens? Oh, up to 2. Okay, so this gives me, you have to go 1 past.
You might even be able to get rid of 3. I don't remember if that works. Like, I think you might just go set to the end.
Yep, that works too. See, it's got a lot of nifty things going on there. Okay, if I want to add matrices, add vectors together, now there's another 4-dimensional vector. If I made this the wrong dimension, I can't add. It gives me some sort of pair, right? So you can only add things that have the same dimensionality. If you want to multiply, this is entry-wise multiplication, right? This is typically not what you want to do. This multiply each entry by doing this star sign. That's why I like to really use something else for the dot product. Yeah.
When you say entry, you mean like element-wise?
Yeah. Yeah. Element-wise multiplication. This was 3 times 1, and it must be 4 times 2, and so forth. Yeah. If I want to do the dot product, there are 2 kind of common ways to do it. Either the array is a special sort of object that has the function dot, so I can do v dot of u, or I can just do numpy array dot, and it takes the 2 elements. These will give me the same answer. Okay, they're doing the same thing. Just different ways of calling it. Okay, now if I have another matrix, now these are not, one is 2 by 3, and this one is 3 by 2. So I can multiply them, and I call this as a dot. It's the same operation. It's the dot product operation. You're just doing the dot product on the different kind of sub-vectors within these matrices. Okay, so matrix multiply is dot products, right? So this should inherently make sense. It's a little bit kind of messier notation than MATLAB, I admit, but it's usually it's fine. Okay, so norms, I can do norms. This is the if I just do norm, it gives me this is the 2 norm. Why is this giving a different thing here? Okay, this is the 1 norm, which is just the sum of all the absolute values. The infinity norm gives me the max, which is 7. The Frobenius norm of and this is, if I put a 2 here, this should give me, right, it's give me the same answer as the 2 norm. So the default is 2, right? The inf norm gives me the infinity norm, which is the max norm. For matrices, I can do Frobenius norm or 2 norm. For some reason, when I tried this before class, it did not take in the fro operation. Maybe I got, I bet one of these was the wrong symbol somehow. I copied this. Let me. Okay, let's see if this works. Okay, good. So that fixed the Frobenius norm. Frobenius norm and the spectral norm of the matrix are not quite the same, but they're close in this case. They're both quantities. Okay, so now you can do transpose of the matrix A. It shows the transpose of a vector. It always prints out a row vector. Okay, it says when you want to print it, you don't want to print a long column vector. It's hard to read. It's easier to read a row vector. It will always print out a row vector. Here, let's say I do X, it gives me the same thing. X and X transpose print out the same way. This is something you need to keep in mind. Yeah.
Even though it's printing it out that way, is it actually really transposing it?
If I were to use it in another operation, then the transpose would be meaningful, but it always prints this way. Usually, if you do like a dot product, you don't need to worry about you're calling dot. There's like should be an outer product operation you can do that instead. It encodes in the operation. This is something that really confused me in writing in MATLAB or C about this. You have to keep the transpose of it straight. Here, you're kind of thinking about it more and more carefully because you're writing dot. It's a dot product. I don't have to worry about how they're stored. And then this is the rank of a matrix. Okay, it was rank 2. I can do, now I need a square matrix to do the inverse. And it did an inverse. If I did this on A, or A, uppercase A, it's not defined because the shape is wrong. Something about it. Okay, so I can't use here, so I have to do a square matrix. And I do C times its inverse. C dot is a matrix multiplication times the inverse. I basically get back the identity. Again, there's super small numerical error. Okay, so but I'm basically getting back the identity matrix here. Okay, so that was basically the main operations we talked through so far. We'll see about computing like the basis and stuff later. We'll see how to do that later in the semester. But you can see this stuff is not that much. It's a little clunkier than MATLAB, but not much clunkier. And it probably might force good habits because of this transpose thing, if you'd like better analysis.
Can you post this note to the website?
Yeah, the code is posted in the book.
Oh, okay.
I don't have maybe I can get the only thing is if you copy it directly, you get these symbols kind of get copied in there correctly, but otherwise it's in there. Just not as a notebook. Okay.
What was that?
Oh, and if you did pick up your quiz, I've got the quizzes up here. So.